This is a video on the simple effective approximation to the square root. And here's the formula. So we want to approximate the square root of x. And in this video, we really look at integer values of x, but it could be for any value. And the approximation is we take whatever x is plus b divided by 2 the square root of b. But b is chosen to be the closest perfect square to x, okay? And I think an example will help illustrate this. So let's say we want to approximate the square root of 77, and we find the closest perfect square. So it's usually between. Now, if this equals a perfect square, well, we don't need an approximation. So 81 is the closest perfect square to 77, so we'll use it in our formula. So the approximation of the square root of 77 is 77 plus 81 divided by 2 times the square root of 81, right? And this is, this is a perfect square, so it's always an integer. So it's 9, 2 times 9. And this is the answer. And you can use just simple, a 4-function calculator to do this. Now, the true value of the square root of 77 is 8.77. And so they're accurate to 2 decimals. And to me, this was so surprising when I first learned of this a couple of days ago. Why does it work? There's no intuitive feel for it. So what I want to do is provide an intuition of why it works, and then look at the errors associated with this estimate. And so this is why it works. So we say that the closest perfect square is approximately equal to the square root that we want to find, right? So in the previous example, the square root of 81 is approximately equal to 71. And that's one of the assumptions. Now, if we subtract root b to the other side, it's this equation. And if we square both sides, we get this. And then if we FOIL this out and then add the negative to the other side, we get this equation. And then if we divide both sides by this, we get the square root of x is approximately this, x plus b divided by 2 square root of b. And that's it. That's the simple intuition behind this. Now, there are some more advanced ways to show that this approximation is pretty close. And I've seen it used with the Taylor expansion, but I actually really think this is maybe a little more simple way to think about it. And here's a big note that will play a part in the rest of the video. In this equation here, we can technically replace that with a greater than sign. And then this is greater than, and then this is greater than. And so our estimate is always above the true value. And and I don't have an equal sign here because x and b are not the same. If x and b are the same, well, we don't need this approximation formula. So they're different. So this is always a value. Could be negative, could be positive. But when we square it, then it's always strictly greater than 0. And so when I see this formula with the greater than sign, I'm still curious about the difference, the error. So the x plus b over 2 root b minus the square root of x. What is this value? And notice I took minus x, right? Because this is always bigger, minus x. And so this is going to be greater than 0. But how small, how big? And so I wrote a program, an R program, to examine these. And you might think, well, why a program? Well, one, because it's easy. And 2, I'll be able to graph the errors, to look at them, to get an intuition. So I wrote a little R script to approximate the square root, using this approach. So what I do is, for any x value, I find the lower and upper numbers that are associated with the perfect square. And then I look at which is smaller. So I'm taking this is the lower perfect square, and this is the upper perfect square. And whichever smaller is the one that we'll use, right? So if it equals 1, meaning this one's lower, then we use the lower perfect number, and if not, it's this one. And then we return this. And it's so cool how that all works. Now, to plot it, let's just plot the first 100 numbers. Remember, so these numbers, the x, we're trying to approximate the square root of x. Okay. And so I use the formula or the function. I go over integers 1 to n, and then that's the approximate square root, using this formula. And then I subtract off the true square root and I plot it. Now, before I plot, you always, I shouldn't say you always, I like to try to guess what's going to happen. And my guess was, as the values of x get larger and larger, that this approximation will get worse and worse, meaning the error is going to grow. That was my assumption. Okay. So when I looked at this plot, I was quite surprised. These are the errors associated with it. Notice that there's no error on the perfect squares, 81, 64, right? Because it's a perfect square, so we don't need it. So there's two things that jumped out in my mind. One is, what is going on with these peaks, right? And also, it looks like that maximum peak is decreasing. So that went against my intuition. And then I thought, well, let's try to prove some of these things. But before we started, I thought, oh, well, the peaks sort of makes sense, because if we're between perfect squares, the worst case scenario is that middle value, right? That, because then that it can't get worse. And so, and that's the case on all those. It's sort of this middle value, and that's the peak. I'm like, okay, that makes sense at least. And we're going to investigate that a little more. But I was really interested, does it go to 0? Now, before we jump in, notice that the parity changes between successive perfect squares. So 1 is odd, 4 is even, 9 is odd, 16 is even, and it goes even, odd, even, odd, even, odd. So the perfect squares alternate. So how many points are between two perfect squares? Okay. Well, it turns out that there's an even number perfectly between them. So not counting the perfect square, and if you count these dots, it's always an even number. And then the same way here, between any two successive perfect squares, there's an even number. But wait, if it's an even number, why is there only one dot? It seems like if there's an even number, that somehow there should be two dots, because this dot is the same distance from this perfect square, and this dot has the same distance to that perfect square. So it seems like the errors would be the same. And then I thought, oh, okay, now I got it. When you look at these and count the dots, those are the two middle values, right? Because there's always an even number of points between any two perfect squares. So those are the two, quote, middle values. But the left middle values is always associated with more error than the right middle value. So here's the two middle values, here's the two middle values. And you'll notice that the right middle value is always slightly more than that one. So those are the two biggest errors, which we thought of intuitively. But that left one is always the biggest, and you can actually you can do some derivations on all the points between two successive perfect squares, and that left middle value is always the largest, always the largest. Okay, so first of all, does the error limit to 0? The quick answer is yes. But now let's investigate. Okay, so here are two consecutive perfect square numbers, and we want to estimate the square root of x such that x is between these. And I probably should say that, x is an integer. I only considered integer values. Maybe in the follow-up, I'll look at continuous values. As we stated earlier, there's always a positive number of points between it, and very specifically, there's 2b points. Remember, these are our perfect squares, and that's how many points are between it. And the way that you do that is you take the larger perfect square minus the second, and you get this number. But when you look at this difference, you're getting rid of that one and everything below, but you're retaining this one, and we want to get rid of it too. So we have to subtract 1, and that's why there's an even number of points. Now, how do you find the middle value between these two successive perfect squares? Well, let's average them. And since this difference, we're taking so this is an even number, an odd number, or vice versa, divide by 2. There's going to be some number here plus 0.5. It's not going to be perfect. So if we have to subtract 0.5 to get to this value, and then we have to add 0.5 to this to get to the right middle value. And then with some algebra, it's pretty simple to show that that's the left middle value, and this is the right middle value. Now, not shown in this video, but I gave a heuristic argument that left one is, I investigated, and it's always larger than the right middle value. In matter of fact, it's the largest between any two perfect numbers, this left middle value. Just to keep the video at a good length, I didn't prove that, but you can easily show that. Okay. So the maximum error occurs at that left middle value. And here, like, this is the left. If we let x1 be the left middle value, this be the right middle value, you can show that the error associated with the left middle value is always bigger than the right middle value. You plug this in for x1, and you plug this in for x2, and then do the math. It simplifies down, and you can show that error on the left is always bigger than the error on the right. So let's examine the limit of the error associated with x1, i.e. the maximum error in the estimate. So we're going to take the left middle value. This is the formula for the square root approximation. Now, right, this is the perfect square closest to x1, and then divided by the square root of the 2 times the square root of the perfect square, which is b. And then we subtract off what the true value is. So we plug in this for x1 here and here. Then this simplifies to this. We just pull that down. 1/2, there's no b in it, right? And we're doing this as b goes to infinity, which means that, x goes to infinity also. There's no 1/2, so we can take it out of the limit, and we're left with this. We multiply it by a well-chosen 1, and it simplifies to this. and then divide the numerator by b and the denominator by b. So it's minus 1, 1, and then you can show that that goes to 1. So it's minus 1/2, so it is 1/2. So the maximum error goes to 0. And that's what we're seeing here. The maximum error between, any two successive perfect squares. Okay. Well, because that subsequence of all the errors goes to 0, that means the sequence goes to 0, of course, as b goes to infinity. And we can show that a little more specifically, and then this is the last formula. So if we have two successive perfect squares and x is strictly between them, and I wish I would have said that x is an integer, because that's the only thing we looked at. And x could be anywhere in here, right? So if x is closer to this perfect square, we use it. And if x is closer to this perfect square, we use it because it's smaller. But for any x, we have to say take the minimum of these two values, which is like saying take the perfect square that's closest to the number we're trying to find the square root of. Now, instead of ranging over all x's, let's just stick in the maximum x, the x that creates the largest error. And then this got a little bit bigger, right? Because we're no longer ranging over all the x's between these two perfect squares. We're just sticking at the largest. Well, we just said the largest was b plus 1. So we put it in for the largest value. Well, and we just showed upstairs that limit goes to 0. So this does show that all the errors tend to 0 as x gets larger and larger. Okay, well, that's all I have for this video. It's about 17 minutes. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.